at the Perimeter Institute, Canada. In August 2020, she led the two-member winning team as a mentor at the World Skills International Competition in Quantum Technology, organized by the Russian Quantum Center in Moscow, Russia. So, Urvashi, I now invite you to chair the session.
Hey, thanks a lot, Kavita. That's very kind that you actually also introduced the chair. I didn't realize that. So thanks a lot for that. And of course, it's a great opportunity to be able to chair this session at QFTA, and it's going so well since morning. So welcome everyone to the afternoon session of QFTA 2020. As Kavita mentioned, we have only one talk in this session as of, because of one cancellation, postponement rather. So it gives me great pleasure, of course, to welcome the speaker for this session, the only speaker for the session, Adan Cabello. Adan, will you have your camera on now? Adan is here.
Apparently,
or not.
I cannot share the video because the host doesn't allow me to do it.
Oh,
now.
So Kavita will
now.
sort.
Good.
Oh, okay.
Good.
Yes,
No.
yes,
Thanks.
great. So so Adan is a professor of physics at the University of Seville in Spain, and of course, I think we all know Adan and his research, his excellent research, which focuses on foundations and applications of quantum theory. So personally, I know him for almost a decade now, and I think I'm also seeing him almost after a decade now. So it's very, very nice to see you. So welcome to this conference, and of course, as always, it'll be a very interesting talk, I can tell you this, this time on converting contextuality to non-locality. So Adan, welcome.
Thank you very much for the introduction, and thank you the organizers for inviting me and giving me the chance to talk here, and for having this initiative in these complicated times. The plan today is to talk about contextuality and non-locality. My idea is to first introduce the theory-independent notions of Bell non-locality and Kochen-Specker contextuality for ideal measurements. Then show how in quantum theory you can convert Bell non-locality into contextuality basically in a trivial way in some particular scenarios. And also you can convert in the other sense, in the same scenarios, but also in a different kind of scenarios, you can make a conversion between contextuality and non-locality. But the main topic today is the following problem. What if I gave you a form of quantum contextuality for ideal measurements? Can you transform it into a Bell inequality, into a non-local game, if you wish? And this is the main task today. But before that, I will introduce the basic notions. I guess everybody knows what is a Bell experiment. In a Bell experiment, you have a number of parties. Here you have two, and each of them has access to a set of measurements. And the game is about measuring on pairs of systems, these observables, and getting the correlations. The notation is the one you have in the transparency. You first have, for every pair of observables, you have a probability distribution. And what we call the correlations in a Bell experiment is a matrix in which in each row you have a probability distribution for one of the context measurements that can be performed at the same time. In this particular case, by the rules of the game, by the assumptions you have in a Bell test, these probabilities, of course, satisfy normalization conditions and no signaling conditions. We are having this talk because in 1964, John Bell noticed that in quantum theory, you can produce non-local matrices of correlations, which are those that cannot be reproduced by local hidden variable models. So for certain scenarios, and in a minute I will detail what I mean by a scenario, you have a situation like this. there's a set of possible correlations that can be achieved through local hidden variable models, which is it's always a polytope. In some cases, meaning for some scenarios, quantum theory allows you to go beyond that polytope, and then you have a convex set, which is the green one. And this quantum set of correlations is inside another polytope, which is the no signaling polytope. Okay. So this is basically my introduction to Bell non-locality. On the other hand, we have a different kind of experiments that I call Koch-and-Specker contextuality experiments, in which you have, in the most general case, a preparation emitting physical systems. Then on these physical systems, you perform a first measurement, but this measurement is not a general measurement, but it's an ideal measurement. In a minute, I will define what I mean by an ideal measurement. This ideal measurement leaves the physical system, and you can again perform a second ideal measurement after the first ideal measurement. And you're assuming that these two measurements are jointly measurable or compatible. Again, I will define immediately what I mean by that. So first, the definition of ideal measurement. What is an ideal measurement? Well, it's an interaction between a physical system, what we call the measure system, and another physical system, the measurement device, that first yields the same result when the interaction is repeated on the same physical system. Second, it does not disturb any compatible observable. By compatible observables, I mean two compatible observables are compatible or jointly measurable if there's a measurement that essentially allows you for any initial state to measure these two observables together jointly. The technical definition is the one you have in this slide. The idea behind the intuition behind the notion of ideal measurement, also called sharp measurement sometimes, is a kind of intuition coming from classical physics, where you have a physical system you want to measure. In this case, it's a piece of wood, and then you have a sort of measuring devices. Okay. So the first condition you ask for a measurement to be ideal is that if you repeat the measurement on the same physical system, you will obtain the same outcome. Here you have a measurement performed at T1, you get an outcome, and then later on you repeat the measurement and you expect to get the same outcome. This is one of the conditions needed. The other condition is that the measurement should not disturb observables that in principle can be measured together. In particular, performing or not the first measurement, in this case, the measurement at the top, does not alter the outcome statistics of the measurement of the bottom. So in practice, if you have access just to the outcome statistics of the measurement of the bottom, you never know whether somebody else have performed the first measurement or not. Okay. So this is the notion of ideal measurement or sharp measurement. And in classical physics, these ideal measurements yield pre-existing results, which do not depend on what we call the context, which compatible observables you are measuring. So this leads us to the definition of contextual correlations for ideal measurements as those that cannot be explained with this assumption of outcome non-contextuality, or this assumption of non-contextual hidden variables, if you wish. In quantum theory, ideal measurements are represented by projectors and are implemented as non-demolition measurements that transform the quantum states according to the Luder's rule. Okay. Again, we will have the notion of contextuality scenarios. And again, a question is, okay, how are the sets of, contextual correlations, of correlations for these scenarios in classical physics or in non-contextual hidden particle theories, in quantum theory and beyond that. And the point is that we have exactly the same geometry as we had in the case of Bell test. On the core, we have the classical set. It's again a polytope. Then we have a convex set. Sometimes we have a convex set beyond the polytope in quantum theory. And outside the quantum set is always another polytope, which is typically called in here the non-disturbing polytope, but it's essentially plays the same role as the no signaling polytope. Good. What are the scenarios? Every time I said the scenarios, what I mean. A scenario is characterized by a number of measurements, their outcomes, and their relations of compatibility. Okay. So my point here is that you can capture, you can encode a possible scenario in a simple graph, which is what I will call a graph of compatibility. Here the dots represent the measurements. They have two pieces, each of them, because they are supposed to be binary measurements or dichotomic measurements. And every time two of them are compatible, you put an edge between the measurements. So you have here a situation with two compatible dichotomic measurements. And for instance, you can define a contextuality scenario or a Bell scenario just this way. Here you have 4 binary measurements with this particular structure of compatibility. So the scenarios are given by graphs of compatibility. In principle, you have as many possible scenarios as graphs you can draw. Okay. And there are some of them, some of these graphs, some of these scenarios that can be implemented both as contextuality scenario or as a Bell scenario. For instance, this one, the square. You can assume that the measurements red and yellow are in Alice side, while the measurements violet and blue are in Bob side. Or you can simply assume that the first measurement can be chosen between the red and the yellow, and the second measurement can be chosen between the violet and the blue. Okay. So here you have a kind of already connection between contextuality experiments and Bell experiments. But we are kind of postponing a kind of basic question, which is, okay, I said, you can have as many scenarios as graphs you can imagine. But the question is, which scenarios can produce contextual correlations, things outside the classical polytope? And the answer to this question actually was known long ago. It's a theorem by Vorobyev that in the modern language said that a violation of a non-contextuality inequality can only occur for scenarios with non-chordal graphs of compatibility, meaning scenarios in which in the compatibility graph, you have induced cycles of size larger than 3, namely squares, pentagons, hexagons, and so on. Remember that the concept of induced graph, a graph A is induced in a graph B. If you can find the graph A by just removing some edges, some vertices and the corresponding edges of B, right? This is a very old result, but this tells you in which scenarios you can have strange things, let's say, because otherwise there's always, and that's the content of this theorem, a joint probability distribution, which in our language means otherwise there's always a non-contextual model. So what about quantum theory with respect to this theorem by Borovjev? Well, quantum theory violates all non-contextuality inequalities that can be violated according to Borovjev's theorem. Moreover, the set of quantum correlations for each scenario is the largest possible one in a probabilistic theory, admitting independent experiments and assigning correlations to all possible scenarios. Okay. So, and within the scenarios in which you can have contextuality, there's a subset of them which is quite famous, which is what we call the Bell scenarios, okay? Or in the language we're using here, the scenarios that can be implemented in Bell test. For instance, in the slide, the one you have as A1 is the two parties, two settings, two outcomes Bell scenario, the square. Here I draw, I don't know whether you can see it, white spot if the measurements are in Ali's side, and black spot if the measurements are in Bob's side. So the second graph of compatibility actually corresponds to the scenario in which you have Alice and Bob. Alice have two settings, Bob has three settings, and well, we assume that the settings are dichotomic, and so on. Here you have 5 examples of graphs which can actually be implemented as Bell tests. But there are many other graphs in which, according to Borovjev's theorem, you can have strange things and classical things which cannot be implemented as Bell test. The simplest one is a famous one, is a pentagon. Okay. Here, the only way to distribute these things in a reasonable experiment is by doing a sequential measurement experiment in which you have a preparation. You can choose the first measurement among the, let's say, the 5 measurements. But once you have chosen the red one in the first place, the second measurement, if you want it to be compatible, can only be, again, the red one or the green one or the blue one. These are the only options here. And there are plenty of scenarios that are like this, that cannot be constructed, or to be more precise, faithfully implemented in Bell tests. Okay. You may say, hey, careful, what about the hexagon there? Okay. Well, the hexagon is a beautiful example of a scenario that cannot be fully or faithfully converted into a Bell test. You may say, okay, yeah, well, I can do that. It's easy, right? Alice has the option of choosing between the red, yellow, and green measurements, while Bob has the option of choosing between the violet, cyan, and blue measurements. But no, this is not really the scenario you have in the graph. What the Bell experiment in the right-hand side is actually implemented is this other graph of compatibility. This is really a scenario in which you can have a Bell test, but not the original one, not the original one. And as we will see in a minute, this creates an interesting situation. Oh, in addition, you have kind of hybrid, what I call hybrid scenarios, in which you indeed can distribute the measurement between Alice and Bob or a number of parties, but then some of the measurements in one of the parties have some compatibilities and eventually can have even by itself a local structure, a local graph of compatibility that allows local contextuality. These things are really interesting. But let's say the overall situation is like this. This one you have in the slide are the contextuality scenarios, the simplest contextuality scenarios, in which in principle you can have non-classicality. And as I said, in all of them, you have non-classicality in quantum theory. Good. So we have on one side the concept of Bell non-locality that applies to a subset of these scenarios. And on the other hand, we have the concept of Cauchy-Specker contextuality, which, well, applies to scenarios which not only with these graphs for Bell scenarios, but other scenarios, but has the restrictions to ideal measurements. So a typical question is, what is the relation between the two concepts, the two theory-independent concepts? And in particular, how to convert one form of non-classicality, let's say, for instance, non-locality, into contextuality, or vice versa. Well, there are trivial ways to do that. Okay. And these trivial ways occur in precisely those scenarios, like the square, that, as I mentioned, you can faithfully implement both as a contextuality experiment or a Bell experiment. Then it's more about how you perform the experiment. Because Bell experiments require space-like separation. So if you add the space-like separation, you are doing a Bell experiment, while contextuality experiments demand ideal measurements, but not space-like separation. My point is that you can move from if you have a situation of a Bell non-locality, in one of these scenarios, you can convert easily into a situation of contextuality with sequential measurements, and the other way, okay? And here, in this situation, every matrix of non-local correlations can be mapped to an identical matrix of contextual correlations produced with ideal measurements. And this is due to an interesting property of quantum theory, which is Neumark dilation theorem. Even if you have a kind of generalized quantum measurement represented by a POBM, there's always a dilation into a projective measurement, producing the same correlations, okay? Which means that according to quantum theory, all the correlations you can have in a Bell experiment can always be produced by ideal measurements. Similarly, every quantum violation of a Bell inequality can be mapped to a quantum violation by the same value of a formally identical non-contextuality inequality. And moreover, a Bell inequality is tight, meaning it's a facet of the local polytope, if and only if the corresponding non-contextuality inequality is tight. Namely, it's a facet of the corresponding non-contextual polytope. Good, this is kind of the trivial case. So let's move on. Let's focus on how to convert contextuality into non-locality. So moving from right to left, in these scenarios that cannot be fully made in Bell tests, faithfully implemented as Bell tests. Okay, for instance, this hexagon. Still, you can get, if you have contextuality in the scenario of the right-hand side, the contextuality scenario of the right-hand side, you can produce non-locality in this scenario, in the Bell scenario, in the scenario of the left-hand side. But the most interesting thing here is that a non-contextuality inequality here might be tight, while in the corresponding Bell scenario is not tight. The most interesting example is the so-called chain Bell inequalities. Actually, the chain Bell inequalities were the first Bell inequalities beyond Clauser-Horst-Shimony-Holt. The chain Bell inequalities were proposed by Pearl in 1970 and then rediscovered by Brownstein and Caves. So they are the first Bell inequalities. But the funny thing is that they are not tight Bell inequalities, okay, for the corresponding scenarios. However, they are tight non-contextuality inequalities for these scenarios, right? So, but now the question is, well, what happened for the other scenarios? Is there any way to convert contextuality for a pentagon into non-locality? And the simple answer is no. There's no simple way to do it. Okay. The question, which is a typical question, how to convert any form of quantum contextuality into a form of Bell non-locality. If you are looking for a simple way to do that, there's no way in general. There are different ways for particular cases. However, this is precisely what I'm gonna do now. This is the new result. Okay, but it's important to understand the philosophy behind this new result. The philosophy is actually the observation that contextuality is mainly about measurements, not about states. The original paper of Koch and Specker, or the original paper by John Bell about contextuality, actually pointed out conflicts between quantum theory and non-contextual models without talking about initial state, just created by the measurements. So within this idea, it's just sort of admitting that, well, state-independent contextuality is actually the core of the thing, is special. Okay, so what I'm going to present is a method. I will present with an example of how to transform state-dependent contextuality into bipartite Bell non-locality. Okay. The method has 3 steps and starts. We are given a set of measurements that we will assume are rank 1 projectors and a state, and we are also said that this state and measurements violate a certain non-contextuality inequality for the scenario defined by these projectors. In this particular case, you have here 5 rank 1 projectors. And if you notice, because of the orthogonality of the states, this is precisely the pentagon scenario, the pentagon of compatibility, okay, which is the simplest scenario violated by the simplest quantum system, meaning the one with the smallest dimension that can produce contextuality. This is the discovery of Kliashko and colleagues. So here you have in front of you exactly that, a violation of the Kliashko inequality. The inequality you have at the bottom is just a convenient form of rewrite the Kliashko inequality. And if you do the calculations, sorry, because I forget to make the calculations, you get a violation here. I think the violation here is, instead of 2, you have 2 plus 1/9, right? Good. We want this to we want to convert this contextuality into a Bell non-locality. So first step of the method is extending the original set of measurements into what is called a minimal critical state-independent contextuality set. Okay, state-independent contextuality set is a set of measurements in which you can produce state-independent contextuality, which means there is an inequality that for any initial state, you get the same violation of the non-contextual bound. Critical, actually the term critical is an invention of Roger Penrose for this state-independent contextuality sets. A set is critical whenever you cannot remove any of the elements without losing the condition of being state-independent contextuality set, okay? And minimal just means having minimal cardinality. Actually, the requirement of being minimal is not that important on the method. Is basically we want it to be minimal for elegance, let's say. So, and what is the minimal critical state-independent contextuality set that has the 5 observables, the 5 measurements I presented before? Well, is the one you can find in the slide. Okay, you add this extra rank 1 projectors, and figure at the left you have the original pentagon, and the original pentagon is just an induced subgraph of this big graph in the right hand side. How can you prove that this is a 6 set? How can you prove that it's critical? How can you prove that it's minimal? Well, in this particular case, a 6 set, the fact that this is a 6 set was proven by Yu and O in 2012. The fact that it's critical can be simply checked by removing any of the elements. And the fact that it's minimal was proven in 2016. Okay. And these proofs are not simple, but my point is that you can do these proofs. Another example of such a proof is the following. This is an example of a Kochen-Specker set, which is also a state-independent contextuality set in dimension 4, discovered long ago. And it has been recently proven that is indeed, well, it was obviously critical, and has been recently proven that is in fact of minimal cardinality. Okay, good. So, okay, and you can ask, how can I do it? Okay, there are methods. There are also all methods that, given any set of measurements, you can extend into a critical 6 set. These methods are easy. Okay, they always work. They don't require big intuition. So trust me on this. You can always easily extend any given set of measurement into a 6 set. Fine. So let's move to the second step of the method. And they said, okay, you have to find the weights leading to a state-independent violation of the non-contextuality inequality you have in the first line, where alpha is the independence number of the graph of compatibility when you put the weights in the vertices. Okay, and you can prove that if your set is a 6 set, there's always a weight such that this inequality is satisfied and violated by quantum theory equally for any initial state, in particular the maximally mixed state, which leads you to this value that I call in the second line Q. Okay, this is the value for this contextuality witness for the maximally mixed state in dimension D. Okay, and there's yeah, this proof is also in an old paper. If your set is a 6 set, weights can be found. Actually, there's a systematic way. It's a linear program to obtain these weights. Okay, so this is not a difficulty. It's not a difficulty to get a 6 set. It's not a difficulty to find these weights. And then you have a quantum violation, state independent of a non-contextuality inequality. But again, this maybe the only way to test this is by doing sequential measurements, right? But first, let me put an example. What are the weights in the case we are talking about? You can prove that if you assign weight 2 to the vertices in black and weight 1 to the vertices in white, then indeed the independence number of this graph is 7, while for any quantum state of dimension 3, you get 7 plus 1 over 3. Good. So, final step, step number 3. Then is basically running the non-contextuality experiment, but injecting not one system of dimension D, but 2 entangled systems of dimension D in a maximal entangled state, and allowing Alice to make the first measurement and allowing Bob to make the second measurement. Of course, Alice just act on the first dimension D system, while Bob just act on the second. And then it's exactly what we call a Bell scenario, a Bell experiment. And I simply rewrite the previous inequality, just noticing that in the previous experiment, whenever you measure one particular projector, you can measure again. Or in this case, Alice can measure and Bob can measure. And then you have the term, the first term in the inequality. And then the second term is basically putting together cases in which Alice measures first, and Bob second, and the other way around. And then the previous non-contextuality inequality transforms into what we call a Bell inequality. It's easy to check that the local bound of this inequality is, again, the independence number of the original weighted graph, which the measurements, the graph that contains the measurements that both Alice and Bob are doing. And it's easy to check that since the initial state is maximally mixed, the local states are, sorry, maximally entangled in this initial state, the local states are maximally mixed. Therefore, the violation you get is exactly the Q I gave before. So you have the same bound, but now it's a local bound, and the same quantum value as before. Good. This might not be what you were looking for, but this method has actually many, many virtues. The main one, I would say, is that it always works. It always works. For any contextual correlations produced by a sequence of ideal measurements, you can do this. And therefore, it allows you to convert the quantum violation of a non-contextuality inequality that might only be testable by performing sequential measurements on single systems that may require very demanding technology into a Bell test, into a Bell inequality that can be tested with local destructive measurements on spatially separated systems. In contextuality experiments, there's one loophole, which is the compatibility sharpness loophole, which is related to the fact that you are asking your measurements to be sharp or ideal, and you are asking your measurements to be compatible as well. I put this slide because this loophole comes together. But in principle, there's no way to guarantee this, neither they are sharp or compatible. You have to check the statistics before getting conclusions. But the issue is that when you transform the contextuality into a Bell inequality, this problem sort of vanishes in the sense that, well, for a Bell test, the measurements can be destructive. They don't need to be sharp. And in principle, measurements in different locations on different systems, especially separated systems, are automatically compatible. So you don't need to do extra tests to check the outcome statistics. Another virtue of the method is that the gap you have between the quantum value and the local bound for the Bell inequality is the same as the gap you have between the quantum and non-contextual gap for the state-independent contextuality inequality. And both are produced using exactly the same measurements. And then is the fact that, okay, if you remove any of the original measurements, then non-locality vanishes. Okay, in that sense, everything that is in the at the beginning is needed at the end to get non-locality. And finally, an observation which is aimed to those that have noticed that for certain scenarios, there's a kind of monogamy in the sense that when you are testing the violation of a Bell inequality and simultaneously a non-contextuality inequality, particular ones, there's a monogamy. Either you violate one or the other, but you cannot violate both at the same time. Well, here you have a situation in which this contextuality non-locality trade-off has vanished totally. You can test together the violation of the Bell inequality, and if you do this violation with ideal measurements, so you can, for instance, in AliSide perform sequential measurements, you can do locally in AliSide also violation of the state-independent contextuality inequality in the same experiments, which is, I would say, nice. Okay, of course, the method is not perfect, because except for the case in which the initial set of measurements is already a SIG set, the non-local correlations resulting from the application of the method do not have the same quantum local gap than the quantum non-contextual gap of the original state-dependent contextual correlations. But, well, in a sense, is a solution to an old problem. And this is the content of this recent preprint. And with this, I'll finish. Thank you for your attention.
Thanks a lot, Adan, for this very engaging talk. So the floor is now open for questions from the audience. Are we raising hands, Kavita, or how are we doing this? Okay.
Yes, they will have to raise hands and then you can call them one by one.
Yeah, so to go through the list, I suppose. I would like to know, Kavita, if you see any raised hand, because I can start the questions then, and maybe Kavita, yeah. Is it right to say that nobody, people are still absorbing the talk?
I thought there would be.
Jaskaran has a question. Yeah. Jaskaran, can you please unmute and ask?
Yeah, thank you. Yeah, hi, Adan. Thanks for a wonderful talk. I have actually two questions. So the first one is it possible to convert any given contextuality graph to extended to a state-independent set?
Yes.
It's always possible, right?
And always, okay. Always. I mean, the difficulties, nice. The difficulties are gonna be, let's say, practical. The first step is you take this initial state and measurements needed to produce the correlations, state-dependent contextual correlations you have. You have to extend it into state-independent set of measurements. And as I said, there are methods to do it for any, but then you can end with a big set. The problem is if you ask the set to be minimal, of course, there's always a minimal set containing your original measurements, but proving that it's minimal can be extremely hard. Okay, but in principle is doable, and always doable.
Okay, so it's always possible to do that. My second question is the pentagram inequality, the Casey-based inequality. Can it be visualized as a Bell-like inequality? I mean, with more than two parties or so on and so forth.
Yeah, this is exactly what I did. Okay, but I start with a violation of the pentagon inequality, a particular quantum violation of the pentagon inequality, and I ended with a particular violation of a bipartite Bell inequality in which Alice is measuring exactly these 5 observables you were using in the pentagon inequality, and Bob is measuring exactly the same thing together with more observables, 13 in total. Okay, so I mean,
but my question was like this. Slightly like, okay.
you start with 5 observables, and you end with
Right.
a Bell inequality in which you have these 5 and the same 5 in both sides, with extra more. They are needed to reach state independency in both sides.
Okay.
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 But it's a bipartite
So,
Bell inequality containing in a critical way the 5 measurements. If you remove any of the measurements, then the non-locality you have at the end vanishes.
I see. Okay. Thank you.
So,
Thank you.
Okay, so we have a question from Professor Dipankar Home. Do you want to please unmute?
Yes.
Yeah.
So Adan, good talk, Adan. So there are a couple of questions. So one of them is that the Kleschko inequality, the argument you give, is it specific to the form of the Kleschko inequality you are using? Or is
No.
it generic?
Okay.
Or it is, but that's not clear from your
very good, very good
put.
question. The argument itself, the method itself is generic. The implementation of the method leads to different answers depending on the particular violation of the Kleschko inequality you are starting with.
Sorry, the generic nature of the argument was not clear from the way
it is generic.
It is generic.
It is generic. For
is it possible?
You start with
what are the essential generic elements you have there?
I mean, it's the same answer as the previous question. Give me any quantum violation of any non-contextuality inequality. Give me that. And from that, I construct a bipartite non-locality scenario that has an essential ingredients in Ali's side and in Bob's side, the same measurements you use in the original non-contextuality inequality. What can be the difference? For instance, let me put an example. The example I put is Kleschko. I start with Kleschko, but notice that I didn't start with a maximum quantum violation of Kleschko. I start with a violation of Kleschko that is not maximum. Why? For, let's say, elegance, because for this particular violation of Kleschko, I can prove that the state-dependent set of measurements that I construct is actually minimal. I can construct the equivalent, one equivalent state-independent set of measurements starting with the 5 measurements that provides the maximum violation of Kleschko. I can do that. But then my resulting set has more measurements and I couldn't prove that it's actually minimal. Okay. Yeah. So depending on the measurements you start with, you end with a different non-locality scenario or situation, let's say. Okay. But it's generic. Generic, not just for Kleschko. You can start with an heptagon. You can start with a very complicated non-contextuality inequality just with sequential measurements. And out of that, produce a bipartite Bell non-locality. But be aware that the final bipartite Bell inequality will have many settings in both sides.
Okay, so the number of settings would be dependent on the form of the non-contextual inequality you are working with. Yes, that's so. Yeah, yeah.
Not only in that, that's true, but not only in that, will depend also on the initial violation. I mean, initial state and measurements you start with. So, for instance, if you start with Kleschko and this violation I present, then it's 13. If you start with Kleschko, but the maximal violation is going to be 30 something.
Okay. But for other inequality, which doesn't work for maximally mixed, because Kleschko works for maximally mixed states. So does it make any difference to your argument?
No, but Kleschko doesn't work for maximally mixed states. No, doesn't work for maximally mixed states.
No,
this is actually something interesting you said, that there's an extension of Kleschko that works for maximally mixed states. This basically the philosophy here. You extend the original inequality and violation into something that is violated also by a maximally mixed state. And there's always a way to do that.
Okay, so that. And another quick question, you talked about the loopholes in the contextuality test, like the compatibility, idleness, and going over to non-locality. But the non-locality experiment itself has those well-discussed loopholes. So what about them that you are?
The detection.
So in that sense, you're replacing one set of loopholes by another set. If one argues, what will be your response?
Yes and no, in the sense that there are loopholes that are common, and you cannot. I mean, the detection loophole is common to contextuality experiments and Bell experiments. The locality loophole is, of course, a specific of Bell experiments, but the compatibility loophole is a specific of contextuality experiments. So you are right that you replace the contextuality sharpness loophole of contextuality experiments by the locality loophole, okay? But we know many ways to deal with the locality loophole, I mean, in principle, and we are not that, not so many ways to deal with the compatibility loophole. So this sort of point out a way to transform, as you said, one loophole here into an easier to fix loophole in the Bell experiment.
And the freedom of choice loophole is common to both, you would say? Or
is common to both, but here, is without invoking relativity. You have to, but yes, it's common. It's common to both.
Okay. Thanks.
Thank you.
So, yes, we have a question from Sarang Bhosle.
Am I audible, sir?
Mm-hmm.
Am I audible?
Is he audible to you? Yes.
Yeah.
So my question is like, it will sound naive than the previous questions, but like, what is the motivation behind converting the non-contextuality into non-locality? And the second question is like why compatibility is coming into the picture? Like, I didn't understand those basic things.
Very good questions, both of them. Let's start with the first one. What is the motivation? Depending on your background, the motivation is one or another. For instance, whenever you are talking about quantum contextuality in front of a computer science audience, they are aware of certain results. For instance, that the presence of contextuality is needed for quantum speed up in certain models of quantum computation. And at the same time, embedded in computer science, even before quantum things, the notion of players game is kind of important, because allows you to identify when quantum resources enter into the game, where exactly is the advantage. Okay, you have a well-defined two-player game, and whenever you play without entanglement, you have a certain performance, but when you are allowed to use quantum resources, you increase this performance. My point is that what are called quantum non-local games are deeply rooted in the way computer scientists analyze quantum speed up. So that's why they typically ask you this question: how can I see this particular form of contextuality into a bipartite non-local game? And this is what the method does, in a sense. So this is one of the motivations. But the other motivation is the fundamental tension on, here you have two resources, contextuality and non-locality, that at least in quantum theory are obviously related. And you can establish, as I presented at the beginning, certain connections, how to transform one or the other. But there's always, I mean, typically you can see many papers that it is impossible to move from contextuality in general into Bell non-locality. And in a sense, it's true. But my motivation is to notice that in another sense, it's not that true. And this is actually my own motivation. In the process of this conversion, you learn a lot. How this is possible? Well, as Professor Holmes' question raised before, you need to go through a process in which you sort of enlarge the set of states that produce contextuality somehow. And then, and only then, you can get non-locality. So you learn a lot about the relation between contextuality in particular state, independent contextuality, and Bell non-locality, which is my particular motivation. And now I go to your second question, how compatibility enters into the game. Well, by definition, in a contextuality scenario, measurements have to be ideal, and correlations are between ideal compatible measurements. But now you go to the lab, and what you have is a source of systems. You perform one measurement and then a second measurement on the systems. How do you know that there are actually ideal measurements? Well, one way to do it is checking that it's actually ideal, repeatable, and not non-disturbing compatible measurements. And now the question is how you check that they are compatible. Well, you can infer whether they are compatible or not by changing the order and so on and so forth, but you need to do extra work. So it was pointed out long ago that one of the loopholes you have, unless you have this extra work, is the compatibility loophole. You cannot simply go to the lab, run the experiment, assuming that the measurements are compatible. Okay, maybe they are not. And you have to fix this issue. That's why the compatibility problem enters into the game. In Bell scenarios, in principle, you don't have such a thing because you are doing local measurements in different locations, which in principle are automatically, at least in the tensor products description, automatically compatible. Okay.
Okay, sir. Thank you, sir.
Yeah. So we have, of course, already extended this session because we don't have a second speaker. So maybe we'll take the last, this particular question from Shumit Mukherjee as the last question then. Shumit?
Yes.
Yeah.
Hello, Professor.
Hello.
Yes. So I have a question that according to your result, we can transform any contextuality scenario into a non-locality scenario. So now my question is that, so in non-locality scenario, we tell something about the quantum system. The non-locality is a essential characteristics of the quantum system, but in a state-independent contextuality scenario, it is the characteristic of measurement operators or what you are measuring, that compatible observables. So if this kind of conversion is possible, then how do you link this property of a quantum system to the property of quantum operators?
Right. Very good question indeed. In Bell non-locality, you need a special kind of states. You need entangled states. So Bell non-locality is resulting from the two resources, entanglement in a particular form and local incompatible measurements. Okay, and out of that you get non-locality. And as you pointed out, in the state-independent contextuality, you don't use states. Okay.
Yes.
So how this is happening? But this is exactly the interest of this transformation. Is the trick is that I use a particular kind of entangled state. It's not an arbitrary entangled state, but it's a specific entangled state. It's a maximally entangled state of two-dimension these systems. This is key, which is what simply allows me to convert anything that is Alice doing in one side and something similar that is Bob doing in another side. Okay. So in that sense, the non-locality I produce is not coming from the state and is more coming from the measurements, which is actually the motivation of originally. Okay.
Okay.
To get non-locality
So-
from the measurements you had.
So if without in any way using the state, can I prove the same thing?
No, you need the state to get Bell non-locality. If the question is, it's also an old question formulated by many people, and well, I don't know. You are somehow asking, is it possible to get a state-independent non-locality? In a traditional sense, no.
No.
It's not. Okay. In some other sense, we've been thinking for a while, but we don't have anything compelling to tell. But is in the standard sense, no. Here you have a set of measurements that produce a state-independent contextuality, and using exactly the same set in two locations, you produce Bell non-locality that has exactly the same gap, quantum versus local, that you originally have locally. Okay, this by itself, this is not the whole method. This is the second and third steps of the method, is also a new result. Okay.
Yeah. So you were saying that in this way, this contextuality is coming from the measurement only. So like say you quantify these things, like one non-locality of quantum system and another thing is contextuality coming from measurements. So is there a trade-off when you are converting these two scenarios?
Yeah, well, the problem is what you lose initially. If, let's say, if you start with state-independent contextuality, you don't lose anything. There's no trade-off whatsoever. The conversion is faithful. Okay.
Okay.
But if you start with a state-dependent contextuality, then you lose the gap, the original gap you may have with a particular state.
Yes.
Okay.
Yes.
In some cases, you can embed the initial state as well and sort of preserve the contextuality or trace back the contextuality, the original contextuality from the final non-locality. But in general, no, that's what you lose. But in case you start with a 6 set, you don't lose anything. I mean, this is a method that transforms any 6 set into a bipartite Bell inequality, proper one, preserving exactly the gaps you have for whenever you use the maximally entangled state between Alice and Bob.
Okay.
What if you use something else is an open question, an interesting one, by the way.
Okay. Yes. Thank you. Thank you.
Thank you.
So I think with that, we will end this session. So thanks, Adan. I cannot help but say that in spite of you being non-local, we have had a very, very nice talk in the current context of COVID-19. So on that rather high note, so although it was one talk, it actually made for a great session. So thank you very much. And I think we reconvene at 5 o'clock, right, Kavita?
Yeah, so
Yes.
I'd like to thank both Adan and Adan for a wonderful talk, and Urvashi for a wonderful chair. We begin, the next session begins at 5:15 Indian Standard Time.
Okay. So